Okay, let's continue on what we learned in class a little bit. We are doing conservation of momentum here. And we're starting out with explosions or things pushing apart. Alright, and we learned in the PowerPoint, momentum is always conserved in this situation. Kinetic energy is not. Alright, important fact. And we talked about this rifle example. We're going to plug numbers into it. We got this rifle loaded up with a bullet, and the two are just pushing apart. Okay, so initially we add these masses. We've got the velocity of the system. In this case, it's going to be 0. This whole side, the initial momentum of the system is 0. Then when they separate, notice the momenta are two separate equations. Okay, so pause the video and plug these numbers into this, and what you're solving for is the velocity of the gun, okay, given the velocity of the bullet and their masses. So pause that and then turn the video back on. We'll do this together. Okay, let's do another similar example. I'll tell you the answer to that in class. Alright, let's do this one. Okay, on this one, it's the same thing. We got two things pushing apart. So you're on a frictionless pond, all right, no friction here. And you've got a bowling ball, 5 kilograms. You're moving forward with the bowling ball at 3 meters per second. So this time the whole system is moving to start. And then while you're moving, you're going to throw it forward. So before, after. What is your velocity after you throw it? Okay. Let's set it up. Anytime we're doing conservation of momentum, we want to start like this. Pi equals Pf for the system. So initially, these two things are together, the person and the ball. So we're going to say mass of the person plus mass of the ball. And I like to put V total, okay, or velocity system. It's the together velocity beforehand. And then after, there's a separation. Mass of the person times velocity of the person. You could put a 2 there if you wanted to, V2 or V final. And then let's do mass of the ball, velocity of the ball. Okay, and now we're just going to plug in numbers. So this time the system is moving, unlike the rifle up here, so it makes the math a little bit harder, but not much. Let's plug in some numbers. We've got 75 kilogram person, and we've got a 5 kilogram ball, and they are moving, we'll call the direction forward +3. Okay, so beforehand the system is moving with a velocity equal to +3 meters per second. Okay, and then we're going to throw this ball while we're moving. This might be fun to go down to the ice rink and try out, take some data, I don't know. Okay, mass of person by themselves, we're going to put 75, and we would like to find out the velocity after the throw. Velocity of the person. Okay, notice that I'm just plugging and chugging here. I'm not rearranging first. I think it's easier with momentum conservation to just plug your numbers in. Your math teacher might not like that, but what the heck. Okay, mass of the ball, we've got 5, and that is thrown forward. In other words, the positive direction, we're calling that 6. Okay, so this goes forward at a +6. Alright. Meters per second. So let's figure out how fast the person's going. Over here we have 80 times 3. Okay. And we're going to subtract this 30 over. So, okay, we got 80 We got 240 kilogram meters per second over there. Then I'm going to subtract my 30 to the other side, so minus 30. I get 210, and my final step is going to be to divide by 75. If you want to show the algebra of that to help it make sense to you, that's fine. And we're going to get the velocity of the person is still forwards, notice, okay? Still forwards, positive 2.8 meters per second. Okay, so they're still going to go forward. That's because they have so much mass that it's not actually going to turn them around. Okay, the more massive this is and the faster we throw it, the more likely the person's going to change directions and turn around there. Okay, it's also notable that this 6 meters per second is with respect to the ground. Okay, and this is with respect to the ground. It's not like 6 on top of the already 3. Okay, that could happen too, but it would have to say that, would have to specify that. Okay, now we're going to talk about the force between the person and the ball. Alright, but first, it's time for a slang flashcard. How about this one, you crazy kids? Trill, what does that mean? Let's check it out. Trill means genuine, authentic, synonymous to gangster. Wow, or from the heart, or considered worthy of respect. Situation you might see this. Nice couple at a salad bar. Okay, and she says to him, when it comes to salad, I keep it trill. Okay, that's a good one. Let's keep it trill and do some physics. Alright. Okay, so this force, this 300 newtons force, it's between them. And remember Newton's third law, that 300 newtons acts on both the ball and the person. So we can do this solving, okay, for time. We want to know how long they were in contact during the actual force of the throw. And we can do that for the ball or the person and we'll get the same answer. Okay, so I'm going to do this all for the ball here. Okay, and this time it's not a conservation of momentum, it's a delta P equals force time problem. Okay, now we know that m delta v is change in momentum. And we're going to set that equal to Ft. We want to know the time that that 300 Newton force acted based on the delta V of the ball. Okay, let's actually divide and rearrange first. So I'm going to say time is equal to m delta V over the force between them. Okay, and again, I'm going to do this all based on the ball. Okay, mass of the ball, 5 kilograms. Okay, in the 10-12 pound range. Okay, the delta V of the ball. Alright, well, we got to look at this. The ball was going 3 meters per second, and now it's going 6. Okay, so our final velocity is what we do when we do final minus initial. We're going to do 6 minus 3. That's our delta V. And our force was 300 newtons. Okay, so we got 15 on the top, 300 on the bottom. Let's divide that real quick. Alright, so we got 15 divided by 300, and we're going to get 0.05 seconds. 0.05 seconds. And you're going to find in these problems with these collisions and explosions, these times are very short, okay? Because it's only the time for which that 300 newtons was acting. It's not the time for, the sliding or any of that, okay? It's just the force between them. One more very important thing we need to talk about with this problem. The things broke apart. Okay, they started out with 80 kilograms going 3 meters per second this way. Even after the throw, the center of mass of the system, which by the way is going to be somewhere right here, close to the person. The center of mass of the person, of the system, still moves in this direction at the original speed as it did before. Okay, and that we're going to talk more and more about that, but what the center of mass of the system does is it stays constant. Okay, here center of mass of the system is going to be closer to the person. It's easy to see that it's moving at 3, but even after the release it still moves at 3 meters per second. Okay, and that's going to come up on a lot of AP multiple choice questions and things like that. Okay, hopefully this added some good examples for you to study some explosions. Next we'll go on to collisions. Okay, thanks for watching.